The purpose of this experiment is to study the motion of objects moving in two dimensions with the constant acceleration, for which projectile motion provides an excellent example. Students will practice how equations of motion are applied in this case and how the different variables of motion are related. For example, students will predict the horizontal range of projectile shot from various heights and angles, and will study the time of flight for projectile shot horizontally different muzzle velocity. Equipment, projectile motion equipment, mini launcher, smart timer, time of flight, two photogate heads, photogate bracket, universal table clamp, metric, measuring tape, carbon paper, and a sandbox. Part 1, motion of object projectile horizontally. Zero launch angle. Check if the angle of the launch is 0 degree. Check that the two photogates are plugged into parts 1 and 2 on the smart timer. Turn off the smart timer using the red select measurement button. Choose the time measurement. Using the blue select model button, choose the two gates mode. This will measure the time it takes the projectile to travel between the two photogates. Check the complete experiment setup in this figure. Zero launch angle. Check the angle of the launcher is 0. Check that the two photogates are plugged into ports 1 and 2 on the smart timer. Turn on the smart timer using the red select measurement button. Show the timer measurement. Using the table select mode button, show the two gates mode. This will measure the time it takes the projectile to travel between the two gates. Check the complete experimental setup in the figure below. Using the crosshairs on the side, record the initial height of projectile edge. In addition, record the spacing between the two photogates. D. Record the value of profile space in table. Place the steel pole into the launcher and use the push rod to load the pole until the one click is heard. Hold the piece of cardboard a few centimeters past the second photogate to block the pole. Press the start button on the smart timer. Pull the launch record on the launcher. Record the time from the smart time display gates. Record the value in the table. Repeat steps 2 to 6 for 2 clicks and 3 clicks. Calculate the initial velocity of the projectile, V naught equal D over T gates, and record the value in the table. Vertical distance over the horizontal distance. According to air resistance, the acceleration A of all projectiles is the acceleration of gravity G equal 9.81 meter per square. Since G is the vertical direction downwards, we set AX equal 0 and AY equal minus G in this equation of motion at constant acceleration. This implies that the horizontal component of the velocity Vx is constant for all projectiles. The horizontal displacement of projectile at time t is therefore delta x equal v naught xt, and the vertical displacement is delta y equal v naught y t minus half gt squared. In this experiment, you will apply these relations to study projectiles with the zero launch angle and with the general launch angles. Motion is as related as the relation is constant and downward. A equal G equal minus 9.81 meter square. The horizontal x component of velocity is constant. The horizontal and vertical motion are independent of each other, but they have a common time. Analysis of motion. Assumptions. X direction horizontal uniform motion. Y direction vertical accelerated motion. No air resistance. Questions. What is the total time of the motion? What is the horizontal range? What is the final velocity? Frame of reference. An equation of motion. This is the table equation of motion. Total time delta t. This is the frame. And y equal h plus half gt square. Finally, y equal 0. 0 equal h plus half gt delta t square. Solve for delta t. Delta t equal square root of 2h over minus g. And delta t equal square root 2h over 9.8 watt meter square. Total time of motion depends only on the initial horizontal range delta x. This is the frame. X equal v naught t. Final y equals 0. Time is the total time delta t. And delta x equal v naught delta t. Delta t equal square root 2h over minus g. And we are put r equal delta x equal v naught equal square root 2h over minus g. Horizontal range depends on the initial height h and the initial velocity v naught. Horizontal through summary. H initial height, v naught initial horizontal, velocity, g equal minus 9.81 meter per square. This trajectory, half parabola open, total time, horizontal range, and final velocity. Data and calculation. Part 1. Zero launch angle. This is table 1. Part 2. Motion of object projectile at an angle. Part 2. General launch angle. Setup. Clamp the launcher to the edge of the table using a vertical table clamp so that the pole launch from and lands at the same elevation. Adjust the angle of the launcher to 25 degrees. Note, with the photo bracket and photo gate attached to the launcher, the lowest angle is approximately 23 degrees. Plug the photo gate closest to the launcher into part 1 on the smart timer. Plug the other photo gate into part 2 in port 2. Turn off the smart timer using the red select measurement button. Choose the time measurement. Using the blue select model button, choose two gates model. This will measure the time it takes the projectile to travel between two photo gates. Part 2. General launch angle. Clamp the launcher to the edge of the table using a vertical table clamp so that the pole launch from the lands at the same elevation. Adjust the angle of the launcher to 25 degrees. Using the push rod, push the pole into the launcher until two clicks are heard. Tape sheet of blank paper at this location. Place carbon paper over the blank paper. Load the launcher. Press the start button on the smart timer. Launch the pole. Use the tape measure to measure the horizontal range are measured. Record the experimental data. Enter the value of the angle in degrees theta, the time between photo gates, T gates, and the horizontal range in meters are measured into the table. Repeat the setup for 35, 45, 55, 65, 75, 85 degrees, using the distance between the photogates and the time between the photogates. Calculate the initial velocity of the ball. Record this value into table. Using the initial velocity and the angle, calculate the horizontal range in meters. Enter this value for each angle into table T. Check the introduction and theory section. Plot both the measured horizontal range R measured various angle theta and the calculated horizontal R range are calculated various angle theta on the same graph. Connect the points R various theta with the smooth line. This is a frame of velocity component. This is degree. Now initial position x equals 0, y equal 0. Initial velocity v naught equal v naught theta. Velocity component x direction vx equal vi cosine theta, and y direction fy f naught sine theta. Motion is accelerated. Acceleration is constant and downward. A equal G equal minus 9.81 meter square. The horizontal x component of velocity is constant. The horizontal and vertical motion are independent of each other, but they have common time. Analysis of motion. Assumptions. X direction horizontal uniform motion. Y direction vertical accelerated motion. No air resistance. Questions. What is the total time of the motion? What is the horizontal range? What is the maximum height? What is the final velocity? Equation of motion. This is a table equation of motion, acceleration, velocity, displacement. Total time, delta t. Y equal v naught t sine theta plus half gt squared. And final height equals 0 after time interval delta t. 0 equal v naught delta t sine theta plus half g delta t squared. Solve for delta t. 0 equal v naught sine theta plus half g delta t. That means delta t equal 2 v naught sine theta over minus g. Horizontal range delta x. X equal v naught t cosine theta. And final y equal 0 time is the total time delta t. Delta x equal v initial delta t cosine theta, and delta t equal 2v initial sine theta over minus g. Then r equal delta x equal 2v initial square sine theta cosine theta over minus g. And that means delta x equal v initial square sine 2 theta over minus g. Horizontal range delta x equal v initial square sine 2 theta over minus g, and conclusion of this horizontal range is greatest for the true angle of 45 degrees. Data and calculation. This is the part 2 general launch angle table. Projectile motion summary. Projectile motion is the motion with the constant horizontal velocity combined with the constant vertical acceleration, and the projectile moves along a parabola.